Hey guys, today we're going to be talking about Lab 5 in Physics 2212, Faraday's Law. So the purpose and concepts of this lab are that we're going to compare the computational experimental data of a magnet falling through a conductive tube. In our experimental state, the conductive tube will be made of aluminum foil. We will also be exploring Faraday's law of a Curly electric field. The physics concepts involved in this lab are the laws of flux, that it equals the magnetic field B times the area of the object, and V equals IR, where I is in current and R is resistance, and V is voltage, or difference. We will also be looking at the Biot-Savart law. In this lab, the experiment was to set up a roll of aluminum foil in the shape of a tube. Then we held a magnet above it and recorded the magnet entering and exiting the tube, taking note of the time stop so that we could see the average time. We did this 5 times to find that it took an average of 1.07 seconds for the magnet to fall through the tube. Next, we created a computational model to figure out what this looked like from the standpoint of code. To do this, we set the length of the tube, the width of the tube, the inner radius, and the total radius, and initialized them. Then, we calculated d flux dt through each ring due to the falling magnet. So, to do this, we took the speed by taking the magnitude of the velocity of the magnet, and then we set a numerator and a denominator in accordance with Faraday's law and the Biot-Savart law. Then we returned the df dt of flux. To continue the computational model, we then calculated the magnetic force from the magnet. To do this, we used the d flux dt function, and then we found the current based on the d flux dt by dividing it by ring in congruence with the Faraday's law. Finally, we computed the typical B field at each ring through the tube. To do this, we used the dipole B function that we had made in Lab 3, and then we crossed this with mu. To do that, we also then multiplied this by the current of the ring and 2 pi the magnitude of the ring, and then that gave us the magnitude of the force on the ring from the magnet. We also found the magnitude of the force on the magnet from the ring. Then we set that to our vector of magnetic force, and then we took the total net force, which is the sum of magnetic force and gravity force. Then we updated the velocity and position of the magnet based on the total net force that we found using the position update formula and the velocity update formula. After finishing the computational model, we ran it and found this graph of velocity versus time of the magnet falling through the loop. On the right is the final of the magnet, where the red is shown at the bottom. According to the computational model, it expected it to take 1.498 seconds for the magnet to fall completely through the tube. So what does the simulation mean? First, we can interpret the color of the simulation. In this case, at the end, red means clockwise current, and blue, while it's not shown here, means counterclockwise current. However, as the magnet falls through the tube, the color changes and we are able to see what that looks like. Also interpreting the simulation, what would the effect of flipping the magnet around? If we flip the magnet around, the current would flip due to the direction of the flux flipping. So then this would affect the total induced current, which would be same magnitude but flipped. Also, if we compare the real world versus the computational model, the difference between them is that the resistance is unaccounted for in the computational model. And if we wanted to make this better, for a future approximation, we would approximate a resistance based on the foil, which is aluminum in this case. So, what does the shape of the velocity versus time plot tell us about the forces acting on the bar magnet? According to this, we see that the net force comes out to 0 at the end, and it's a total sum. Also, we see that acceleration stops when constant terminal velocity is approached. Finally, when looking at this, we ask what if? What if the resistivity of the conductor were reduced to as close as possible to 0? If this happened, the current would increase with flux, so the force would increase and decrease overall velocity. If we increase the force and decrease overall velocity, that means that it would take the magnet longer to fall. However, what if slots were cut into the tube then it would decrease the total magnetic force, so then the magnetic field would become weaker. And as accordance with our position update formula, that means that the magnet would fall faster. Thank you for watching.